Hello, welcome to another lesson. Today's video is actually going to be fairly short. I'm only going to cover maybe 5 or 6 pages, just because the next video picks up from page 22, I think, and I don't want to overlap. So here we go. This is picking up right where we left off. You might remember this, assuming that this is your class, of course. Page 15. We had a lot of fun, good memories, just before Halloween. Finding the result given the Boolean state, true or false, 1 or 0, and given these expressions. So in these exercises, exercise 2, we're just going to get some practice with 1s and 0s, just because it can be useful to know kind of what to do when you have 1s and 0s. Well, first of all, 0s are what you should look for first, because if you add 0 to something, for example in this case, it's as if the 0 was never there. You can essentially cancel it as soon as you see plus 0. And in another case, when you have multiplied by 0, they cancel the whole expression that's being multiplied, all right? So expressions tend to simplify down quite quickly once we see zeros. So that would be my biggest point of advice here. Look for your zeros first. And the answers we're going to get are going to be 1, 0, 1, 0 in order for 1, 2, 3, 4. All right? So shout out to Adam King for reminding me about looking for the zeros first, because that's a useful thing for students to know. And of course, brackets. So let's do the first one, 1 plus 0. 1 plus 0 is 1, right? Think of it as the 0 doesn't matter, it just kind of cancels out. So that whole bracket is done. Multiplied by, what's the other bracket? 1 plus 1. 1 plus 1 in Boolean is 1 or 1. 1 or the other is 1. Of course, 1 or the other is 1. So it gives a truth value or a 1. In other words, 1 plus 1 caps out. There is no such thing as 2 in Boolean, so 1 plus 1 must be 1. 1 times 1 is 1, also known as 1 and 1. 1 and 1 gives a value of 1, so that's why this might be something you want to keep in mind, how it works. Question 2. Let's see, we have an entire bracket being ANDed with a 0. Right away, if you get that, if you see that that 0 is there, this whole thing gets destroyed. The entire statement gets what's called annulled. So there's an annulment going on. When you multiply by 0, the entire expression gets deleted, because anything and 0 must be 0. You can't have something times 0 to give 1. Or in other words, in order to get an AND, 1 and 1 is 1. 1 and 0 is 0. 0 and 1 is 0. 0 and 0 is 0. As soon as we see a 0 with AND, we're going to get these zeros, okay? So for many reasons, anything multiplied by 0 is 0, and in Boolean it's no different. But let's just say you didn't notice that. So let's see what would happen. 1 plus 0 in the brackets gives a 1 plus 1. 1 plus 1 in those brackets. 1 plus 1 is 1 in Boolean. And 0 and 1 is 0. So in a couple different ways, we see that the answer must be 0. Let's try number 3. Again, you should pause the video here and try these yourself. They're not long, but you can get a good sense of accomplishment if you try it and you get it right. I'm going to look at the 2 brackets. In the first bracket, I have no zeros, so it's just 1 plus 1. 1 plus 1 in Boolean is 1. So this equals 1. And 0 plus 1. Again, if anything plus 0, anything added to 0, is as if the 0 was never there, so this gives us a 1, and 1 times 1 is 1. In other words, 1 and 1 is 1. Looking at 4, it looks quite long and complicated. Let's see if we can make our lives easier. Well, I see a 0 here, 0 plus. Anything or 0, well, the 0 doesn't help. 1 times 0 is going to be 0. 0 times 1 is going to be 0. So these are going to come out to 0 and 0. And the 0 in the first case here is as if it was never there. Let's see what we've simplified. So the square bracket, 1 times 1 in that bracket gave a 1. Multiplied by, let's see, we've got a 0 plus a 0 in that bracket. I'm just keeping the square brackets there just for a bit of structure. You don't need them, strictly speaking, but it's a good idea to keep them as long as you can. Here we have 1 times 0 plus 0, 0 plus 0 being 0. So really we have 1 times 0, which is 0. Now, there are many ways to approach this. Different people have different strategies or points of view on how it should be done. The only thing I'm going to ask of you is show enough steps. Don't skip too many steps. And the reason I'm saying don't skip very many steps is because at the end of this problem, problems like this, you can only get 0 or 1. So you have a 50% chance of getting the final answer right, but if I can't go through your logic and say, yeah, everything checks out, everything makes perfect sense, I can't give you that mark because you might have gotten a 1 or a 0 as your answer by accident, and that's not okay. The whole unit is about logic. I mean, it's Boolean algebra, but that's based on logic. I need to be able to see exactly what you've done and know for sure that you know what you're doing. Okay? So that's my little spiel on that. Let's move on. What do we have next? Evaluate the expressions using Boolean algebra. I'll leave these for you to try. Oops. I'll leave these for you to try because they're basically the same as what we got before. I'll write the final answers out here just for you to check it against, but you should try these yourself. All right. Moment of truth. It's 1, 1, 1, 1, 1, and 1. Okay, so all of these work out to 1, but it's up to you to see why. All right, and something that you might want to remember at the end of the day, for all of these, and this will come up a lot more at the very end of this unit, anything plus 1 is 1. Or in other words, anything or 1 is 1. Okay, something to keep in mind. This should help you out for these types of questions. But see if you can get 1s for all those. So page 18 is just this optional mini assignment. So what I've said is go to this website or a website like it. So you can use academo.org or you can use my personal favorite now, which is logic.ly/demo. That's the one that I've been using most recently to present a given practice question as a logic circuit and then share that with me. So you can share it with me by email, send me a picture of it. You can even drop it in a Dropbox or something, but probably easier to do it by email. And then I want you to create your own statement and create its logic circuit and then share that with me. So you have a choice. I mean, first of all, let me be clear, you don't have to do this assignment at all. But if you'd like some extra practice, you can either present a practice question. What I mean is take one of these, make it circuit, and send it to me. Or create your own statement. For example, maybe you want to make this statement, you make your own practice problem, make it circuit, and then share that with me. If you do that, if you make it and you share that with me, I'll give you 1 bonus mark. So that maybe if you lose a mark on a test sometime, you lose a mark on an assignment sometime, I will take that mark, I'll toss it on, and I'll give you a bonus. All right? But at the end of the day, completely optional. But let me just show you how you would do this assignment if you choose to do so. In this case, we have 1 plus 0, which is the same as 1 or 0. So how that manifests itself in this question is you would have a switch coming in that's on, and another input or switch, which is off. That's your 1 and 0. And you mix them together, or put the both inputs entering an OR gate. Right? They both go into an OR gate. Then, for the other situation, you have an off, or an on, and then they would be coming into an OR gate. So in this case, I've actually made a little mistake here. That should be a 0. So 0 and 1, 0 and 1, are coming into an OR gate, which is why we have 0 or 1. So the result of this is 0 or 1. The result of the first one was 1 or 0. And then you have 1 or 0 as an input, coming together with 0 or 1 as an input, and the gate itself is an AND gate, which is what that dot is, okay? So this is a little bit of foreshadowing as to what we're going to do next, like following this introductory set of gates for this unit. But again, optional assignment. If you want to do it and you send me something like this, that would be great. I'll give you a bonus mark. If not, no harm done. And the final output is indeed 1. It turns on. Okay, so I made a typo here that you might want to catch, but hopefully you see the purpose of the assignment. I know you're busy, but it might be nice for you to try the assignment just to get that extra easy mark for later, just in case you need it. So the following section, I'm just going to introduce this today, and we'll continue it in the next video, is showing how Boolean expressions can be represented as circuits. I gave you foreshadowing about this before, but it's a good idea to take a look at it now, kind of in a formal way. So what does it say? Boolean expressions can be represented as circuits. So expressions can be represented as circuits, also known as networks, also known as, well, there's a lot of different ways you can say it, but we can just say it looks like a circuit. And they have to include these three things. At least one input, each of which can be 1 or 0. So in this case, this is 1 input. In this case, it's 2 inputs. This would be 2 inputs. So I could probably write this down just below. This would be 2 inputs. This would be 2 inputs. And this would be 1 input. That's the first case. That's what you need for a circuit. The second step would be at least one logic gate. So in this case, we have 1 gate. In this case, we have 1 gate. And in this case, we have 1 gate. I mean, it's kind of pointless to have a circuit that doesn't have a gate in it at all. At least for Boolean algebra, we definitely want to have at least 1 gate. And then third situation, we need to have 1 final output. So our output is represented by this light bulb here, okay? The output in that case was, in the first case would be output of 0. The output here would be output of 1. And output here would be output of also 0. So what it says is which Boolean expression is represented by each circuit below. So I'm actually regretting writing all of this extra annotation on this because I've muddied it up. So I'm going to erase it. It's no problem if you keep it there, but I'm going to erase all these extras just because I've made it more difficult to see the point of the question. I'm sorry about that. I should have thought more ahead. Which Boolean expression is represented? Let me show you how to do these. Let's say the first input is A and the second input is B. And this gate here, what kind of gate is that? You know, think to yourself. Pause the video if you need to. Say, which gate is it? This is an AND gate represented by the dot. Okay? So you have an A input coming in. You have a B input coming in. They're being joined by the gate. They're being tested by the gate. That means we have A and B, which can also be written as just AB, by the way. But for our cases, we're going to say AB. That is our whole expression. So below this, we can just say the expression is AB. Put the dot in the middle if you want or not. Okay? If you wanted to make a truth table for this, the output would be something like 0 and 0 give a 0. But you don't need to write that. So I'm going to erase it now. I just want you to think ahead to that. Second case. Pause the video, see if you can figure this one out. What's it going to be? Me looking at this, I say right away that this is A or B. How do I know that? I know that this is A and this is B. That's just standard. They're being joined by an OR gate. That means we have A coming in and B coming in. It's A or B. Once again, you've got A coming into it and B coming into it. It doesn't really matter what the state of it is yet, on or off, but we know they're both going in, they're being joined by an OR gate, so A plus B. That means the output finally would be a test of A plus B. If you did want to think about the outputs and inputs, see if they make sense, this would be a 1, a 0. 1 or 0, what output does that give? Well, it actually gives a 1, so the light bulb's on. That makes sense, hopefully. In our last case, let's say our input is A. What kind of gate is this? Well, that's what we call a NOT gate. That's our negation, that's our complement. That takes the input and makes it opposite. So you'll notice that the input here is 1, the output coming out is 0. It's flipped it. Flipped it. So if the input is A, a NOT gate means not A. There are multiple ways you might see this. You might see it as a tilde A. Sometimes you'll see it as, I don't know the name of that symbol, but you'll see that A. Sometimes we even say A with an apostrophe, or what looks like an apostrophe. So different ways to write the same thing. It all means not. So, for example, if you have a 1 coming in, yeah, you have a 0 coming out. And we talked about that quite a bit in class. If you want to write it as part of the circuit, you would say A, not. If A plus B was going into it, for example, you would negate that, and it would be not A or B. So for the next exercise, one of the last things we're going to do today, it says write the Boolean expression represented by each circuit, check your answers using truth tables. And it reminds you in the top here to write the expressions properly, use A and B for inputs, use plus for or, use multiply for and. Pause the video and try these, okay? Try both of these, see if you can get them. They're not difficult, we've done them before. This is almost a review as much as anything. So it says check your answers using the truth table. We'll check the truth table after to check if 0 and 1 does give a 1. Okay? So this is the solution. A, or you can put A here, A and B. A and B coming together. This is an OR gate, which means it's A plus B. So our final expression is A plus B. The truth table is written for you, or at least it's set here for you. You just need to fill in the blanks. So this is A plus B, also known as OR. 1 1 0 0 1 0 1 1, or sorry, 1 0 1 0. 1 or 1. 1 plus 1 is 1. 1 plus 0, 1. 0 plus 1, 1. 0 plus 0, 0. What expression is being represented here? We have a 0 and a 1 for A and B. It's this. 0 and 1 being our inputs. It's being our output. Does this make sense? 0 and 1 give a 1. Is that true? 0 and 1 give a 1. Yes, it is true. So I've checked that my output is okay based on the inputs. So let's see that I've answered the question just so you can follow me here. Write the Boolean expression represented by each circuit. That's this piece. Check your answers using truth tables. I checked my inputs, I got the correct output, and so I'm finished my question. Once again, pause the video, see if you can get this one. What I say is A and B in the beginning. This looks like an AND gate to me, which is a dot. A and B with a dot in the center, A times B. My truth table then, or my expression, will be the expression for A times B, or the table for A times B, also known as AND. Maybe I should write that below. I'll write that AND here, and I'll go back and write the OR here just to have full notes. Let's do our truth table. 1 1 0 0 and 1 0 1 0. Multiply them. 1 times 1. 1 times 0. 0 times 1. 0 times 0. And finally, let's check to see if what we were given, 1 and 1, give a final answer of 1. Is that true? 1 and 1 give a 1. So our truth table is giving us our appropriate answers, or is matching our inputs and our output. Hopefully it's clear what I'm trying to accomplish here. I'm just trying to show you that the truth tables are a way of representing one of many possible states, and the gate is just a way of testing the inputs versus the output. And there are many, 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 many gates, and we can mix them all together if we want to. So that's what we're going to do now. So for exercise 2, and this is the last thing I'll do in this video, not and, NAND, not or, and NOR. So not and NAND, not or, and NOR. Turns out they're going to mean the same thing, but let's see that with help from an example. Same situation as before. We're going to write the expression and make the truth table. So this is A, this is B. What kind of gate are they going into? Well, they're both flowing in to an OR gate. You don't need to write the plus, you don't need to write the OR. I'm writing it there to help you understand. So we have A and B coming in, and it's coming into an OR gate. That's the connective. If A or B flows into a NOT gate, the whole expression is negated. This is extremely important. The order here is extremely important. You can't negate something unless you have an expression first. So you have a plus b, and then it's negated. All right? You might not see that as a bit of a problem. That might not even seem confusing right now, but I have a lot of students that when given a plus b and I ask them to draw the circuit, they'll take a and negate it, and take b and negate it, and they'll put those both into a OR gate and think that that's a plus b all negated, and that's absolutely not what's happening. This would actually be negated a or negated b. That's not the same. Okay, so I don't want you to write any of that down unless you want to write a little note to yourself about that. But little foreshadowing for later, be really careful about the order in which things go into gates. So at the end of the day, I've actually already written my expression. It's right here, but it's a good idea to write it out clearly at the end. A plus b negated, not and or b. Turns out it's going to be called NOR. But let's do our truth table. A and b, 1, 1, 0, 0, 1, 0, 1, 0. A or b. Okay, let's do this piece first, the first piece of the gate. Add them together, a plus b added together. So 1, 1, 1, 0. Negate that, because we want our final answer, right? We want not a or b. We don't want a or b. We want not a or b. So we need to negate what we've been given. You take all these responses, all these outputs, and negate them in that last column. So just flip them. 0, 0, 0, 1. Finally, we're going to check our results. 0 and 1 apparently gives a 0. Is that true? 0 and 1 gives a 0? Yeah. That's exactly what we expected. That's what we want. We can even check this 1. Can you think how maybe you'd look at that diagram and figure out if it's a 1 or not after the OR gate? Take a moment to think about that. Well, it's represented by this wire right here. That wire, it looks like it has current flowing through it. Or if it was water, it has water flowing through it. That gate is open, or in other words, it's on. It's a 1. So we can see if we trace through this, this is a 0, this is a 1. After the OR gate, we get a state of 1. If it goes through a NOT gate, it gives us the opposite, which is the 0, which is the same story being told here. 1 and 0, when going through an OR gate, give a 1, and when followed by a NOT gate, give a 0. It's kind of neat how you can see all the different connections once you get used to this. Let's do the last one of the day here. What do we have? We have A and B flowing into this gate. What kind of gate is that? It's an AND. Remember, the AND gate looks like a D shape, which is the same as the last letter in AND. The OR looks like an arrowhead. This is A and B. It flows into a NOT gate, or a negation. So it's A and B, A or B, A and B negated, not AB. Also known as a NOR. Oh my god, I'm mixing up all my words. Sorry, it's also known as a NAND. But we will get to that a little bit more a little bit later. Now we'll do the truth table. 1, 1, 0, 0, 1, 0, 1, 0. By the time we finish the truth table, we're going to be able to represent this situation in the table somewhere. It'll already be done by the time we finish. A times B. So what's 1 times 1? 1. What's 1 times 0? 0. 0 times 1? 0. What about 0 times 0? 0. Now we negate it, because we want our final expression, remember? AB, negate that. You can put the dot or you can not. Up to you. Negate AB. We have AB. Negate it. 0, 1, 1, 1. So there's a few things I've missed. I didn't actually write out the final expression, so I probably should have put that here in the middle. And now I just need to check that the diagram matches my table. I need to find the state that it's talking about. So here I have a 1 and a 1 going into an AND gate. A 1 and a 1 are giving a on state, or a 1 out of it. But then that 1 is being negated, turning into a 0. can I find that story in my truth table? Turns out I can. 1 and 1 are coming together, giving an on state after they've been put through the AND gate. That's this situation. But the final output is really what I care about, and it gives a 0. So at the end of the day, I have found that combination in the truth table. And I could have asked for any combination. This is just one particular example. Alright, so that's actually all we're going to cover in this video. Like I said, it's going to be a shorter video than normal. But hopefully it made sense. I just wanted you to get a good feel for how you build the expression given the circuit. Instead of, just working with the tables, just working with expressions, just working with, little pieces, I wanted you to see how everything came together in a really formal, structured way. And what we're going to end up doing, first of all, we're going to do more practice building these expressions, more and more and more. We're eventually going to see that NAND and NOR are gates that we can build, which is just not and not or. We're going to talk about exclusive OR, which again is an expression that we've talked about before, or at least foreshadowed. And then eventually, after we do some summary, we're going to make the circuits ourselves. All right, so lots to look forward to. But, I hope you enjoyed this video. I hope it made sense to you, and we'll pick it up where we left off in the next video. Have a great day.